Now we come to the last part of the lecture. We talked about a number of different actuators and actuator materials, but some of them are require materials that are not quite common in CMOS processing or in MEMS processing, such as, for example, magnetic materials, shape memory alloy materials, other phase change materials, or piezoelectric materials. And then, of course, the question is, how do you integrate such materials into a MEMS structure? There are basically four approaches one can follow. So how to get the high quality material onto the microstructure. So there's basically four approaches, and actually you have them here. The first is to do a micro part assembly, part by part. The second is to adapt the material so it becomes compatible with CMOS processing or with MEMS processing. The third is heterogeneous integration or transfer bonding. And the fourth is make composite incorporation. So let's talk about the first. The first is integration of actuators as part by part. And here's an example of a plastic microvalve that is actuated using a shape memory alloy structure on top of the spring. And this is manufactured actually in a way where the plastic parts are molded separately, and then the entire structure is piece per piece packed together. The advantage is that, of course, it allows you to get a very high quality material, like a bulk SMA material in this case that you machine, and to have this very high quality material and integrate it onto the microsystem. The disadvantage is, of course, that you have a part per part assembly, which becomes often very costly. And also, it's difficult to downscale this, like down to the micrometer scale. And also, the packaging and gluing of the structure may pose specific problems. So basically, what you're doing in this approach is that you shift the problem from developing compatible material deposition techniques to a assembly and packaging problem. Second approach you can use is to use the actuator materials, but adapt the materials such that they become compatible with the CMOS processing or the MEMS processing that you're using. An example of such a strategy you can see here in a micrometer chip from a DLP projector, where you have micromirrors that are made of small aluminum mirrors that can tilt. So aluminum is a rather okay mirror material. However, it will be sensitive to plastic deformation. So what you actually would like to have is an absolutely elastic material that will always move back to the same state. But in this solution, they have actually used aluminum because you can deposit at lower temperature, and it comes at the cost that you have a certain plastic deformation. You don't get the perfectly flat structure and not the perfect actuation behavior. However, for this specific application, it works very fine. Other applications where you need micromirrors, where you need to, for example, an extremely good control over the reflectivity and over the nanometer precise position of the mirrors, there you cannot use aluminum. So there this approach cannot work. The third approach, and this is an approach that has been pioneered and developed to a large extent at KTH in our lab, is that of heterogeneous integration through transfer bonding. So what you do is you have your MEMS material, microstructured material, and then you have your high quality material. And you combine these two on the wafer level or on the sheet level by using bondings, typically adhesive bonding. So what you do is you spin a very thin adhesive layer and you glue. It's basically gluing together the things, and then after gluing, removing the handle wafer of one of them and then making the interconnects. The advantage of this approach is that it allows batch integration, thus it's going to be cost efficient. Disadvantage is that this technology is not yet mature, and so there is some further development necessary, and also you shift your problem to a very good adhesive bonding and dealing with that, and so it is a complex step actually to do. It's only one step. You do maybe 1,000 devices in one step, but it's still a complex step that is prone to error. A fourth alternative to incorporate high quality materials that works for some materials is to make basically a composite material. So you use that's not possible for all materials, but for example, say you use a metallic powder and you mix that into polymer, so you make a composite. And then, for example, if that's a magnetic powder or a low reluctance material, you create a spinnable polymer-like material that actually has a low reluctance also. So the advantage is it allows batch integrations. You're spinning on of a mixture. The disadvantage is you need to be able to turn your high-quality material into composite and still retain the material quality. And that may be also tricky for some. So for example, shape memory alloys, we have tried that. We haven't found a way to do that, for example. But for example, magnetic materials, this is a way you can work.